All right, I'd like to finish talking about the longest common subsequence problem, which we started in class. Now, this is the problem where you're allowed to take any subset of characters in sequence, but you can leave blanks. So if I have the sentence, rules are not all that great, actually rules are great is a subsequence of that. I just skip a whole bunch of characters. I don't have to skip them in order though, so Ursinus college students are great students also contains rules are great. Now if we think about the two of those, we can create binary strings to represent each one. So representing that subsequence and rules are not all that great, I put a 1 every time I take a character and a 0 every time that I don't take a character. And here's what that would look like for Ursinus college students or grade students. So I could think of representing each subsequence as a binary string. That's one representation I could use. Problem is, if you want to look through all binary strings and compare them, there's exponentially many binary strings of a particular length. So if there are n bits, there will be 2 to the n possible binary strings. So then you're arguing if a string has n characters, same thing. There's going to be 2 to the n possible subsequences. So that means I'm looking at an exponential time algorithm, which is not what we want. So then in class, students had some really interesting ideas about, okay, what if they tried to walk through the characters starting at the beginning and tried to match them? So if I started walking through rules are not all that great in Ursinus college students or great students, I might start and say, okay, I have an R here. Let me try to walk through this until I find an R. Okay, as soon as I find an R, I match them. Okay, so that worked pretty well. So once I match them, now let me move on to the U here. I'll keep walking until I find a U. Okay, that works pretty well. So now I can move on to an L. Let me keep walking until I find an L. Nice, found that one. Now I've got an E. Let me keep walking until I got an E. Well, I'm going to match this E here. Is that the right thing to do? I don't know. That wasn't the same E that I was indicating before. But you can run into an even worse problem if, let's say, I reverse these strings. Let's say I start walking along this one first. Let me say, okay, I want to keep walking until I find a U. So I'll do that until I walk. Okay, I find a U. Now let me move on, and I'll walk until I find an R. Okay, I skip over all this stuff, and then I find an R. So now I've got U, R, and look at all this stuff I missed that I knew could have matched. So if I'm too greedy, and this is the first string I look at, and I say, let me try to find a U, then let me try to find an R, I'm going to miss a whole bunch of stuff. I think it's even easier to see if you do it that way. So you could find a subsequence that matches that way, but it's not necessarily going to be the optimal subsequence. And the problem is you're making these what I call greedy decisions without having the foresight to know how that's going to impact you down the line. So you could be setting yourself up for some trouble in the future. So it's actually better to work backwards. Because if I work backwards and I say, okay, does the S match the T? No. Does the T match the T? Yeah. Okay, maybe I'll try to match those. I know that there's nothing else I can do. So if I match the last characters, that was it. I know that I'm not going to mess myself up later on. So if I work backwards, I have a hope of doing better. So that's what I'm going to try to do. So first, rather than actually coming up with the optimal substrings, let me just try to count the length of the maximum substring. Oftentimes, when you count a solution first, or you compute an optimal cost, it's just one more step to actually extract that optimal sequence. So if I pass in 2 strings and I want to just know the length, okay, well, I'm going to make some kind of recursive thing because I'm going to work backwards and then do something recursively. So first of all, my stopping condition, if either one of the strings has 0 length, then I better just return 0. Okay, because if one of the strings is empty, the biggest the biggest subsequence I can get from that string is empty. So that's not going to help me. But otherwise, let me work backwards. So let me show an example, a couple examples I was looking at in class. So one of them was school versus fools, and the other one was, or let me say school versus fool, and the other one was phone versus phones. Okay, so on the first one, school versus fool, the last characters do match. So I better include those in the subsequence. So I'll say if S1 -1, so the last character of S1 is the last character of S2. Then what I can do is return 1 plus, well, now I'm going to recursively call this because I'm going to try to match everything else. So I will remove these two characters because I know I'm going to include them and match them. And let me try to match everything else that came before that. Okay, so that's the recursive call there. Now if they don't match though, I can't add 1 to the maximum, right? I'm not going to match those two. The question is, what do I do next? So if I look at the phones versus phone, I try to do a similar thing. Okay, I chop off the S and I chop off the E and I keep going. Now I'm going to be matching phone to phone. Okay, well, E doesn't match N, so I'm going to chop that off and keep going. Okay, now the N doesn't match the O, and you can see what's going to happen is I'm not actually going to match anything. I'm going to think that this is 0. So I have to be careful. I shouldn't cut off both characters. And what I should do is just cut off one of the characters and then recursively match. But I'm not sure which one to cut off, so I'm going to say, well, let me make this the maximum between the longest common subsequence if I chop off the last one of the first string, but match the entire second string, or I do match the entire first string, but then I have to chop one off of the second string. Okay, so that's it. Now, this is going to be very slow. There's overlapping subproblems here. You know, if one thing I could do is chop off the S and then match the E's. But as I'm doing my recursion, I also could have chosen to chop off the E, then chop off the S, then chop off the E, and in both cases I end up at fon. So you're going to see there's a lot of overlapping subproblems. So we're definitely going to want to do memoization. But first, let me just run this brute force. It's kind of a brute force recursive implementation with no memoization or anything. So if I do the longest common subsequence between phone and phones, well, I should get 5, right? Okay, good, because phone is a common subsequence there. Just to show you that this works even if I add a space there. Okay, right, because remember, subsequence doesn't have to take everything in a row. Now if I do school versus fool, I should get 3 with that ool at the end. Alright. But this is slow. So first, let's do memoization to speed it up. Okay, here I am 2 years after I recorded this initial video. And I realized that the way that I was explaining memoization back then is not the way that I actually want to teach it now. I had updated most of my other content, but it looks like I forgot to update this video. So, just to quickly tell you what I'm actually looking for, let's review memoization for the Fibonacci sequence. So normally I would define the Fibonacci sequence recursively like this. You know, I would say maybe the base case, the result is 1, but if n is greater than 2, so after the first 2, actually, so 2 base cases here, n equals 1 and n equals 2. But if n is greater than 2, then I'll say the result is fib of n minus 1 plus fib of n minus 2. And I'll go ahead and return the result there. So just to show that this works, let's go from 1 to 9, and I'll print the fib of that number. And so we get the first 10 Fibonacci numbers, or first 9 Fibonacci numbers. But this is not the best way to do it because there's a lot of overlapping subproblems. And so what I was showing you to do before is use a dictionary. And by default, it's empty. But what I'll do is before I compute anything, I'll say if n is in the memory, then, actually maybe we'll say, yeah. So if n is in the memory, then I will pull it out, and I won't bother to compute it. But if it's not in the memory, and I actually have to do some work, then I will compute it. I'll be sure then to remember that this solution evaluated to that particular result. I meant to say, whoops, memory end. Okay, there we go. Okay, so this is a way to go up much higher in the Fibonacci. You wouldn't be able to go this high before, because it was just branching out too much with these overlapping subproblems. So I'm looking for something similar here. Notice the pattern was check once at the beginning if my problem has already been computed. And then otherwise, we have to compute it. Compute the solution, but don't forget to store the solution in the memory so we don't have to repeat it again. So one hint, so same kind of thing here. There should be one if statement right at the beginning to see if these strings have been computed before, and one if statement at the end. Now my hint is, we kind of talked about this for edit distance in class, but there's a couple of ways to use a key in the dictionary to store which problem you're looking at. So this is a little bit more complicated than the Fibonacci sequence because we actually have two inputs. But we can index the problem by a key that is a tuple, which is the length of the first string and the length of the second string. That tuple uniquely identifies which subproblem we're looking at. In class, we talked about some other options. Somebody else came up with the idea of S1 plus underscore plus S2. That would work just fine. You could also do, you could actually just do S1, S2 in the tuple. So whatever the strings actually are straight up. But the nice thing about this one is it's pretty concise in memory. It's just two numbers, the length of the first string that you have left and the length of the second string. So that's what you should use to index the problem in your memory. So just like the Fibonacci, you'll first check to see, hey, have I seen this problem before? If so, let me not recompute. Let me actually pull out the result and return that. Otherwise, I will do all this work, but I'll be sure to remember the work that I did and store it in the memory. Okay. Now let me just cheat really quickly. I have two really long strings here that are just not going to work without memoization of some sort. So I run this, it's going to go on forever, practically. Actually, though, this is not what you're going to do on the module, but I figured I would show you. Once you've gotten used to this pattern, there are some memoization tools built into Python. So if I say from func tools import LRU underscore cache, another way of describing a memory or memoization is as a cache. We're caching the previous computations so we can quickly look them up again. And then you put this what's called a decorator on top of the method. So I'm going to say, okay, I want to use a cache for this method. And I'm not going to limit how many results I can store in the cache. And so now it computes in no time. It's doing memoization and we get the answer here. But in the module, I'm going to have you implement that manually. Okay.